So when two waves interact with each other, you add the amplitude of each wave at that point in space, and that gives you the new value of the wave. So for electromagnetic radiation, it'll probably be the electric field. For water waves, it will be the height of the wave. And for sound waves, it'll be the pressure of the air. In any case, you add them together, so that means that if the value is positive for both or negative for both, it will increase the magnitude of the amplitude of the wave, and if one wave has a positive value and the other a negative, then the magnitude of the wave will decrease. So that means that two waves can positively reinforce each other, or they can cancel each other out. So the term for this is this positive reinforcement is a constructive interference, and if it's canceling each other out, then it's called destructive interference. So the interference effect is most noticeable when both sources of light are monochromatic. That means they have the same wavelength, and so they are the same color. It also is much easier to see when the light is coherent. Coherent light is when the phase of the electromagnetic radiation is all the same. This means that the peaks and troughs are all lined up. This is most common in lasers, where the light is all produced with the same phase. Okay, so let's take a look at an example of constructive interference. In this case, I guess we're looking at sound waves, but the concept is the same. So we have two sources of coherent sound, two speakers that are the same distance from a person's ear, and presumably they're playing the same note. Since the wavelength of the two waves are the same, that means that they stay exactly in phase with each other and they are perfectly in sync. So if we added the amplitude of the waves together, we would get a sound wave that has twice the amplitude. So if the waves are in sync, then the interference is constructive. A second example, we move the speaker by exactly one wavelength closer to the ear. So now the difference in the path length is equal to exactly one wavelength. So what happens when we move the speaker forward by exactly one wavelength is that the waves are still in sync with each other. If we move the speaker forward towards the ear by another wavelength, so now the second speaker is two wavelengths closer to the ear, then the sound waves are still in sync, so once again the interference is constructive. To figure out what kind of interference we have, what we'll do is we will take the difference in the path length. So how far does the first sound wave travel to the ear? How far does the second sound wave travel to the ear? So we will take those two distances, and then we're going to subtract the distance of 2 minus the distance between 1. So then, in this case, the distance to the ear by the first speaker minus the distance to the second speaker is 2 times the wavelength. Next, we divide the path length difference by the wavelength, and we find that this m value is equal to 2. So as long as m is an integer, so if it's 0, 1, 2, etc., then the interference will be constructive. So long as m is an integer, and so the difference in path length corresponds to the wavelength times some integer, then the sound waves are going to be perfectly in sync with each other, so the interference will be constructive. So what happens if they're not in sync with each other? So for destructive interference, the condition is that the difference in path length is off by 1/2, one integer minus 1/2 times the wavelength. So in our example here, our second speaker is 1.5 times the wavelength closer to the ear than the other. That means that the peak in the first sound wave is a trough in the second. So if you add them together, they're going to add up to be 0. So that means that they'll cancel each other out. You won't hear anything. So if the difference in path length is off by an integer minus 1/2, so in this case m is equal to 2, then the path length difference would be 1.5 times the wavelength. And so our integer is 2. 2 minus 1/2 gives us 1.5, and the difference in the path length is 1.5 times the wavelength. So that's going to be an example of destructive interference. So if we move one speaker closer, and if it's, as long as it corresponds to 1.5 times the difference in the wavelength, then you're going to have destructive interference. Okay, so the sound sources aren't usually placed, kind of right next to each other like that. Usually what happens is they are separated, and we're looking at a point in space to figure out if the interference is constructive or destructive. So the distance from our first source to P1 is this length 1, and the distance from our second source to P2 is length 2. So basically we would take the longer, so L2 minus L1, and then we would divide by the wavelength to find out if the interference is constructive. If that number is an integer, so 1, 2, 3, 37, whatever, then the interference is constructive. And if we find m using the formula for constructive interference, if the value is an integer minus a half or plus a half, then it is destructive interference. So if it was 1.5, then we would know that it's destructive, and we would use our formula to find that m is equal to 2 for the destructive interference. So let's say our light has a wavelength of 500 nanometers, and the path length of L1 is 1500 nanometers, L2 is 2250 nanometers. So then we would subtract them, so 2250 minus 1500 is 750 nanometers, and then divide by the wavelength, and that would give us 1.5. So that means that we have destructive interference, and the 1.5 is equal to m minus 1/2, so m would be equal to 2. Okay, so now let's look at our FET. So this will be posted after the video, so you should take a look at it and get a better feel for what's going on. So we're going to drop 2 droplets at the same time into the water, and they're going to make a wave. So I'm going to drop 1 here, and so what happens is the light blue corresponds to a peak in the wave, and then a black spot, so that corresponds to a trough in the wave. So now I'm going to add a second droplet. There we go. So now that we've added a second droplet, we can see that an interference pattern is starting to form here. So I'm going to put the marker here, kind of where the destructive interference is. So notice if we look straight down the middle, so here the path length difference between both of the 2 points here, so that's going to be exactly the same. So that means that there's going to be constructive interference down the middle. We're going to look at this angle. We're going to call this sort of an angle theta, and this is going to correspond to destructive interference because there's a path length difference when we're traveling from the spot where one droplet goes to the other. So we can see this interference pattern forms, and so the difference in the path length in the 2 droplets is going to be an integer minus 1/2 times the wavelength. So so also notice that if we look straight between the droplets, the path length there is the same, so that means your interference is going to be constructive. Your value of m is 0. So what happens if we start to change the wavelength? Well, first let's increase the wavelength. So if we increase the wavelength, in order for the interference to be constructive, that means that you have to travel a larger difference in order to have a difference in path length. So that means that the theta value here becomes larger. And if I decrease the wavelength here, so if I decrease the wavelength, then that means now our interference patterns, they move a lot closer to each other. And so this is because the wavelength is smaller, then it can more easily interfere with each other with a smaller difference in the path length. So now, what happens if we change the distance between the drop points? Well, if we move them closer to each other, so let's see here. All right, so I've moved them closer to each other, then the path length difference is smaller, so the waves are going to need to travel a further distance in order to have a difference in path length, so our theta is going to get larger. And if we move the drop points away from each other, so we separate it, so if I separate it, then that means that the theta gets much smaller, so it creates a much stronger interference pattern. So we can also do this with light. So let me switch here. There we go. So if we do this with light, we can, it works pretty much the same way. So let's see, if we decrease the wavelength, so I'm going to make this blue, So that means the pattern gets much closer together. And then if I switch to a longer wavelength red, then the interference pattern moves further apart. So just like we did with the droplets. And then we can do the same thing. We can move them further away from each other to get this pattern. And then, in the wrong one. And if we move them next to each other, so then the theta gets much larger, the interference pattern moves away from each other. So what this means is that the wavelength and the spacing, they are proportional to each other. So this wavelength and theta are proportional to each other. And then the relationship between the distance between the light sources and the angle theta, well, that's going to be inversely proportional. Okay, so you have a few questions to answer, and next we're going to look at the two-slit interference experiment. Good luck.